Hi everyone, this is Mrs. Jackson. This is Chapter 2, Section 3, Part 2. So far in this section we've learned how to solve for the zeros of a quadratic function. In other words, solve for the x-intercepts and use those intercepts to graph the function. In this second part we're going to be looking at how to write the function when given the zeros to start out with. So let's take a look at a specific example here. If we have an x-intercept of -3 and another one at +2, if you recall the way we would solve those, if I said x had a factor here and somehow I get -3 out, then that factor would be x plus 3. And same here, to get +2 out as my solution or my zero, then my factor must be x minus 2. So that's one potential function that we can write that yields zeros at -3 and +2. Now if I go ahead and distribute that, I'll show that. Everything's got to distribute. So if I go ahead and write that out in standard form, I would have x times x is x squared. I have a +3x, a -2x, so that's going to result in a +1x, and a -6. So in this function, a equals 1, b equals 1, and c equals a -6. So that's our most obvious function we can write that have zeros at -3 and +2. However, that's not the only function. In fact, there's an infinite set of functions that we can write with the exact same zeros. So for example, I could multiply my factor x plus 3 by 2 and make that 2x plus 6. And maybe I'll do the same thing with the x minus 2 and get 2x minus 4. And this function would absolutely have the same exact zeros. It would have a 0 at at -3 and a 0 at +2. However, you can see when we multiply or distribute everything through, it's not the same function. So 2x times 2x is 4x squared. I have 2x times a -4, which would be -8x, plus a 12x would be a +4x. And a +6 times a -4 would be a -24. Since I decided randomly to multiply both of those original factors by 2, you can see that these are related. So our original function here and this function, this one is a multiple of 4 times the original one. However, you can see in this one our a factor, which is our stretch, our a equals 4. And that's certainly going to be a much taller and skinnier parabola that goes through the exact same zeros. And so on and so forth. I can multiply through any random number that I want to. Let's try 3. I'll just do the first one by 3. So I'll end up with 3x plus 9. I'll keep the second factor, x minus 2, what I had in my original. And if I multiply that through, I end up with 3x times x is 3x squared. 9x minus 6x is +3x. And 9 times a -2 is -18. And here you can see in this resulting function, because I only did the first factor by 3, this one is a complete factor of 3 by the original. I could also, and by the way, let's just put a pin on that. That's a stretch factor of 3, so it's also taller and skinnier, still upward facing, but has the exact same zeros. Now I can multiply through by a negative number and actually have a downward facing function. So what if I took the first one and multiplied that through by a -1? I could say -x minus 3. That's still going to result in a -3, 0, and I'll leave the first one the same, x minus sorry, that's not x minus 2. If I multiply that through, I have a negative x squared. I have a positive 2x, and a negative 3x would result in a negative x. And a negative 3 times a negative 2 is a positive 6. So you can see here that this resulting function is the original multiplied by a negative 1. So this would be a downward facing parabola, a equals negative 1, but it has the exact same zeros. So just to put a visual to that, what we did here is we said that we had zeros at negative 3 and positive 2. There's an infinite number of parabolas that can go through the same zeros with different stretches, including downward facing parabolas. So just knowing those zeros alone is not enough to write the function. We can only write a generalized family of functions. But in our observations, we did see that the family did have something in common. They were all multiples, some kind of multiple, positive or negative, of the original most basic function that we could write with those zeros. So the way we can write that in a generalized sense is the following. We can put some kind of scale factor here in the front, which of course we always call a, and put a placeholder in here for our zeros. I'm going to use just two variables, p and q. So a is our vertical stretch or compression, depending on its value. And essentially that can be divided out, right, of each function in the family. P is one of the zeros, or x-intercepts. And Q is another zero. And so we can generalize this way. And for example, let's take a look at this. The directions say write a general equation for a family of quadratic functions that have zeros at negative 2 and negative 5. Well, if we have a zero at negative 2, that means our that means our factor is going to be x plus 2. Likewise, our other factor, if I have a 0 at negative 5, then my factor would be x plus 5. And then we have some kind of multiplier up front here, and that would be our generalized family. However, if we had to write a specific one function given the zeros, then we would need another point on that function to determine the one unique function that can describe that. And so in this example down here, we're told that we have zeros at negative 3 and positive 1. So if we have a 0 at negative 3, that would be a factor of x plus 3. And if we have a 0 at positive 1, that would be a factor of x minus 1. And we're going to have some kind of stretch or compression up front. And that's going to be our function. If we want to go beyond generalizing the family and actually find out what the stretch is, we need a point. And here we're told that point 5, 8 is, oopsie, I don't want my highlighter. 5, 8 is a point on our function. So the 5 is an x and the 8 is a y, and I can substitute that in. So I'll put in for my output here, f of x is my output, it is my y. I can substitute 8 in there, and I'll put 5 in for my x. So I can solve for one unique function and get my stretch factor. So here I have 8 equals a times 8 times 4. 8 equals a times 32. And divide by 32 both sides, and I get 8 32nds, or 1/4 of a stretch factor. So bring that all together now and write that final function. For this specific example, we would have f of x equals 1/4, that means vertical compression, times x plus 3 times x minus 1 is our specific one unique function with this set of attributes. So I hope this video helps you to determine what the function is when given the zeros. Thanks for listening.